In this class, we will highlight some important facts concerning test statistics, and we will then discuss how we can use the T-statistic to construct a confidence interval. Before leaving the t-test, it would help to notice both the structure of the t-statistic and what the structure tells us about the nature of test statistics. You may have noticed that in each case, the t-statistic has a statistic of interest in the numerator and the standard error for that statistic in the denominator. Thus, for the two independent samples t-test, we have the difference between the independent means in the numerator, each of the means in the numerator, and the standard error for the mean differences in the denominator. Similarly, for the dependent samples t-test, we have the mean of the difference between change scores in the numerator and the standard error of mean change scores in the denominator. Also, in each version of the t-statistic, we have an estimate of the effect of treatment in the numerator and an estimate of sampling error in the denominator. By the treatment effect, I mean the test statistic is attempting to assess the effect of the independent variable on the dependent variable. In tests of means, we do that by evaluating mean scores. And in the t-test, we evaluate differences of a single mean from the population, the differences of two independent means from each other, or the mean of change scores, or the difference between scores pre-test and post-test. Because a good bit of the research is focused on clinical interventions or treatment, we can think of the numerator of a test statistic as telling us about the effect of having participated in a treatment versus some other situation. In the simple example we have followed in this series of classes, the effect of treatment has contrasted the mean of individuals who participated in treatment for depression versus those who did not, or contrasted the means of the same participants before and after treatment. So the major theme to learn from all this is that all test statistics we will study in this class are ratios of treatment to error. Thus, when we obtain a t-statistic of 4.5, we mean that our estimate of the effect of treatment was 4.5 times larger than our estimate of error. Up until now, our focus on the t-test and other statistics has been for the purpose of hypothesis testing. But another important issue in statistics is using statistics to estimate the population parameter. If you will remember from one of our first classes, we discussed that statistics, numerical characteristics of samples, are used to make estimates of parameters, the numerical characteristics in a population. By using what we call a confidence interval, we'll be able to construct a range of values likely to contain the value in the population. Basically, the confidence interval is the formula for a t-test merely written differently. What we do is to take the statistic of interest, such as the sample mean in a one-sample t-test, or the mean difference score in a two-sample t-test, and to that we both add and subtract the product of the standard error for our statistic and the critical value we use to test a hypothesis. Because the critical value is based upon alpha, 0.05, the confidence interval we are usually most interested in is the 95% confidence interval. If you'll recall from an earlier class, 1 minus alpha is called the confidence of a test. We will interpret the interval that we derive using this formula as follows. We'll say that we are 95% confident that the interval we just constructed is one likely to contain the population statistic of interest. Let's learn about the confidence interval by revisiting the samples we used earlier in the class. For the one sample t-test, we said that the sample was found to have a mean Beck depression inventory of 12 and a standard error of 2.2. When the sample size was 25 with the degree of freedom 24 and the critical value was t equal to 2.064. Before going to the next slide, see if you can compute the 95% confidence interval for these. The 95% confidence interval is computed by taking the statistic of interest, here the sample mean, and we then add and subtract the product of the standard error of the sample mean and the critical value. Thus 12 plus or minus 2.2 times 2.064, which is 12 plus or minus 4.54, resulting in a confidence interval of 7.46 and ranging to 16.54. We would interpret this by saying that we were 95% confident that this was an interval likely to contain the mean of depressed individuals who received treatment. Before going to another sample, notice an important fact about the confidence interval we constructed on this slide. Namely, it does not contain the mean of the BDI in the population of 17, which you recall was the null hypothesis for a t-test. Thus, a confidence interval also gives us information about the results of our hypothesis test, with a basic rule of thumb being that if the value associated with the null is not contained in the confidence interval, we reject the null hypothesis. And if the value associated with the null is contained within the confidence interval, we retain the null hypothesis. In this situation, the value associated with the null was 17. Because that value is not within the range, we would reject the null hypothesis. Thus, when we retain the null, we are saying that one of the possible values of the mean in the population is the value associated with the null. And if we are rejecting the null, we are saying we are 95% confident that the true confidence interval does not contain the value associated with the null. Before going to the next slide, let's revisit the example we used for a two-tailed t-test. In that example, we have 30 depressed individuals randomly assigned to two independent groups, one who received an experimental treatment and another group that received no treatment. At the end of treatment, the mean of the treated group was 12, the mean of the control group was 20, and the standard error of mean differences was 2.50. Because n equaled 30, degrees of freedom equaled 28, and from the table, the critical value was 2.048. Before going to the next slide, see if you can compute the 95% confidence interval and determine whether or not you would reject the null based upon the confidence interval. The confidence interval is 2.88 to 13.12. This was computed by taking the statistic of interest, the mean difference score, plus or minus the product of the standard error of the mean differences and the critical value, or 8 plus or minus 2.5 times 2.048, which will equal 2.88 to 13.12. We would interpret this finding by saying that we are 95% confident that this was a range likely to contain the population mean difference score. As we discussed in the earlier slide, when the null hypothesis is that means are equal, it also follows that the difference between the means should be 0. Thus, 0 is the value associated with the null hypothesis. Since 0 doesn't fall in the confidence interval, we would reject the null hypothesis. Now, let's try the example we used for the dependent samples t-test. In that example, we had 30 participants who all received a treatment and were measured twice, once before the treatment and then after the completion of the treatment. The pre-test mean was 24, the post-test mean was 12, and the mean of change scores was 12, and the standard error of the mean of change scores was 3.5. Because n equaled 30, degrees of freedom equaled 29, and the critical value was 2.045. Thus, before going to the next slide, compute the 95% confidence interval for these data, and determine if the null should be retained or rejected based upon the information in the confidence interval. The answer is that the 95% confidence interval is 4.84 to 19.16. This was computed by starting with the statistic of interest, the mean of change scores, plus the product of the plus and minus the product of the standard error times the critical value for these data. So 12 plus or minus 3.5 times 2.045. We would interpret this interval to mean that we are 95% confident that this is an interval likely to contain the mean change score. As discussed earlier, if the null hypothesis were true, there would be no difference in change scores, or the value of d bar in the population would be 0 if the null were true. Because the confidence interval does not contain 0, we'll reject the null hypothesis. If the confidence interval had contained 0, or the lower bound of the confidence interval was negative and the upper bound of the confidence interval was positive, we would have retained the null. Before going to the next slide, see if you can answer this question. If the standard error increases, what will happen to the confidence interval? The answer is that as error increases, the confidence interval increases. Thus, as error increases, our ability to pinpoint the population value is less and less precise, or we need a broader range. Similarly, as the interval increases, we run a greater danger of including the value associated with the null in the range. This is another way of saying that as error increases in a study, our test is less and less powerful, and the risk of making a type 2 error is greater. Let's test this out. Before going to the next slide, create a 95% confidence interval using the data from the last slide, but this time substituting the standard error of the mean change scores that is 2 times larger, increase it by 2 times to 7. The confidence interval is now negative 2.33 to 26.325. So we take the statistic of interest, our mean change score, plus or minus the standard error, which is now 7, times the critical value. Notice that the interval is much broader, and we are consequently less able to be precise about the value of the mean change scores in the population based on this experiment. In addition, the interval now contains the value associated with a null, or 0, indicating we are no longer able to reject the null hypothesis.